When you compute a limit, it is fundamental that you are able to compare different quantities, and in particular to analyze the magnitude of quantities involved into a limit. This means, for example, imagine you have two quantities, two sequences, for example, that they are both going to plus infinity. It is important to be able to establish which one goes faster at plus infinity. Now, here in this video, we will focus on a particular comparison between two standard quantities. On one side, we will consider a power n2 exponent alpha, where the exponent is chosen positive because we want that n2 alpha goes to plus infinity. And on the other side, we have an exponential, a to power n, with a strictly greater than 1, again, because we want that this quantity goes to plus infinity. Actually, here we have infinitely many powers, because for every value of alpha, we have a power, and here again, we have infinitely many exponentials. But let's say a generic power versus a generic exponential. Which one goes faster at plus infinity? Well, before we give a precise definition of what does it mean that a sequence goes faster than another sequence at plus infinity, we do a little experiment. We will do a sort of race between these four quantities. Here we have n squared, n cubed, which are 3 powers, versus an exponential 2 to power n. What we will do is to compute these four quantities for the first 10 values of n, basically. And this will allow to do a certain number of remarks and to guess what could happen for n big. Of course, if I consider the first 10 values of a sequence, this is not at all saying anything about what happens for n big, for n going to plus infinity. Nevertheless, in this case, we will see that something interesting can be guessed from this behavior, and then we will take this as a general statement later. So let's start with the race. For n equals 0, n squared, n cubed are both equal 0, while 2 to the n is 2 to 0, 1. For n equal 1, again, n squared and n cubed are both equal 1. 2 to the n is 2 to 1, 2. So basically nothing is happening the first two values of n. For n equal 2, something changes because you see n is just behind of the other 3. N squared and 2 to the n are more or less at the same point, while n cubed seems to take the head of the race. And this is confirmed by n equal 3, where we see again n squared and 2 to the n more or less at the same point. N cubed is far, is going faster respect to the other two, and then is just behind. This is again confirmed by n equal 4. Now imagine that we stop here with the race, and we look at this situation. We would say that n cubed is going faster than all the other, n squared and 2 to the n are going at the same speed, and n is going slower than all the other quantities. Of course, this conclusion would be false, because when n is 5, we start to see that 2 to the n takes an advantage on n squared, and this advantage becomes more clear for n equals 6. You see that the value of 2 to the n is basically 2 times the value of n squared, or if you want, n squared is 1/2 more or less 2 to the n. This ratio becomes even smaller the next value of n, because here we have 49 versus 128, and n equal 8, 64 versus 256. So it's getting smaller and smaller. So what about n cubed now? As you can see, at n equal 8, n cubed is still ahead the other 3 quantities. But if you observe what is happening to the values of 2 to the n, you see that they are growing, yes, and they are reducing the gap to n cubed. If you take the ratio, you see that here n cubed is basically 3 times 2 to the n. Here we are about 2 times. Here we are slightly above 1 time, and for n equal 10, the ratio is 1. For n equal 11, you see that the ratio has reversed, because now n cubed is basically more or less 1/2 of 2 to the n. And if you continue like that, you will see that the ratio n cubed divided 2 to the n will be smaller, will become smaller and smaller. And the guess would be, reasonable guess is that the ratio is going to 0. So this makes also clear what should be the idea of something going faster than something else. We should say that something goes faster if the ratio between these two quantities, the slower and the faster, is small. Now, the guess at this point should be reasonably the following. An exponential goes always faster than a power. Now, this is actually true, and it is the content of this statement that says that when you compute the limit of a power n to alpha with exponent positive over an exponential a to the n with basis greater than 1, we get always 0. To get 0, it means that this fraction becomes small, and since the two, numerator and denominator, are big, this means that the denominator must be much greater than the numerator, so another order of magnitude with respect to the numerator. Now, I will not prove this statement here, but I will, in general, but I will show you just a particular case, which is the comparison between these two quantities. On one side, I will consider the exponential 2 to the n, and on the other side, I will take the power n. And our goal is to check that, to verify that n over 2 to the n goes to 0. So now to do this comparison, we need somehow either to write the power as an exponential or to write the exponential as a power. And this is what we do. And the idea is a little bit tricky because it consists in thinking to 2 as 1 plus 1. So you write 2 to the n as 1 plus 1 to the n. And then the next step, the key step, is to write this using the binomial expansion, which is in general a plus b to power n is equal a to the n plus n times a exponent n minus 1 b plus n times n minus 1 divided to a n minus 2 b squared, and so on, until you finish with b to power n. Now, this is the binomial expansion. The remarkable thing is that if you plug here a and b equal to 1, you see that these factors are always equal to 1. So you get 1 plus n minus 1 over 2 plus etc. Now, look at this formula. And stop just here after the first few terms. So you see that 2 to the n is 1 plus n. So here we see that 2 to the n is greater than n because all remaining terms are positive. In this formula, everything is positive. Actually, these are natural numbers. These are numbers that you can find in the Tartaglia triangle. So now, you may notice that 2 to the n is not just equal to 1 plus n because there is another term here, plus n times n minus 1 divided 2. And this one is not only positive, it is of the size of n times n. So it is an n squared. So that's why you understand that the size of 2 to the n contains not only n, but also n squared, here n cubed, and so on. So it will be greater than n. So this gives the idea of what we have to do, because if we write this fraction as n over, we copy this, 1 plus n times n minus 1 divided 2 plus many other terms. We notice that since all these quantities, 1, n, and all terms here are all positive things, if we just eliminate them, we reduce the denominator, and this means that we increase the fraction. So this will be less or equal than n over n times n minus 1 over 2. We can simplify this n here, and what we obtained is that this is less or equal than 2 over n minus 1. So our quantity, which is here, n over 2 to the n is less or equal than 2 over n minus 1. And of course, it is greater or equal than 0. So our quantity n over 2 to the n is between 0 and this guy. These are the two policemen that go to 0, because 0 is constant equal to 0, it goes to 0. 2 over n minus 1 is going to 0. So the two policemen go to 0, therefore n divided 2 to the n, who is in the middle, will go to 0 as well. And this explains why this is true, at least when a is 2 and alpha is 1. What are the next steps? Well, first of all, you should practice the comparison exponential versus power by computing some limit, like, for example, those I wrote here. A further step, which is actually a technical step, is to do the same kind of problem, but where you have some parameter inside, like here. So this is a more difficult problem because you have to consider different cases. You will have a behavior for certain values of a, another behavior for other values of a, and so on. A more advanced step is to try to prove the comparison exponential versus powers in general. This is a technical problem, in fact. It's not a theoretical problem, but you have to try to adapt the idea I presented here in this video for the case n versus 2 to the n, and try to adapt when you have an exponential base a. So start comparing n or n squared to a to the n. So the idea you have to use is to write this exponential a to the n as 1 plus, since a is 1 plus a minus 1, so you have 1 plus a minus 1 to power n. And then use the binomial expansion and try to repeat the same kind of argument we did. So next step, you replace power, like n squared, to a generic power n to k, where k is a natural exponent. And the last step will be to do in general with an exponent alpha strictly positive. It is not easy. It is a little bit technical, but it is a nice work that you can do to, if you want to challenge yourself with a more advanced problem. Have fun.